Hello all, good morning. This is Dr. S. Subbalakshmi, Assistant Professor at the Department of Mathematics, SNS College of Technology. This is a lecture video series on the course Probability and Statistics, and now we are on to the topic Design of Experiments, under which we are going to see problems regarding one-way ANOVA classification. One-way ANOVA classification can be restated as completely randomized design here. So in this video, we are going to see the procedures or the steps involved in proceeding with the problems of one-way ANOVA classification, which is completely randomized design. Previously, we have seen the conditions, terms and terminologies used in the ANOVA classification and what is analysis of variance. And today we are going to see the procedure for it. The step number 1, we will be usually framing the null hypothesis. This null hypothesis H0, it is denoted by H0, wherein we will be saying there is no significant difference between the columns and errors. There is no significant difference between the columns and errors as usually mentioned here. And in the second step, we will be having the alternative hypothesis. What is our alternative hypothesis? Alternative hypothesis is there is a significant difference between the columns and errors is our alternative hypothesis. In the third step, we will be finding the number of given observation with the number of given observations and see the total number of samples given. So what is n, the number of given observations, and what is c, the number of samples given. And in the fourth step, we will be finding the total number of summation of the given items, which is denoted by t, wherein t can be denoted as summation of x1 plus summation of x2 plus etc. till how many values of the items we have. The fifth step is a very important step to overdo with, which is the correction factor. The correction factor is equal to t squared by n. What is t squared? What is t? We have already found it in the previous step, and what is n? That also we have found it in the earlier step. And this is what we are going to use as a procedure, because in the previous step, what all the things we have found, will be implementing it at the corresponding step. So that the correction factor is equal to t squared divided by n. And in the sixth step, we will be finding the sum of the squares of the treatments, which will be denoted by S and T. T, which means sum of the squares of the treatments, it is equal to summation of x1 square plus summation of x2 square plus summation of x3 square plus, again, the correction factor here is very important, because if we leave the correction factor or the error occurred in the particular thing, we will be recurring an error over the procedures followed. And in the steps number 7, we will be finding the sum of the squares of the columns, which means how many columns we have in the given problem can be depicted here as n. And in here also we will be reducing the correction factor here. The correction factor plays a predominant role in all of the procedure steps. And in step number 8, we will be having finding the mean squares between the samples, which is denoted by m, s and c, which is equal to sum of the squares between the samples divided by the degrees of freedom. Degrees of freedom is nothing but we have already seen how long extent that particular thing can be taken up on hand, which is equal to SSC by degrees of freedom, which is equal to SSC by c minus 1. And then the final step, to find the mean sum of the squares with the samples, which is mean sum of the errors, MSE, which is equal to sum of the squares within the samples divided by the degrees of freedom, which is denoted by SSE by DF, and it is given by the degrees of freedom for this particular error is n minus c, and that is denoted as degrees of freedom. So here, and also we are in need of finding SSE. What is SSE? Which is nothing but SST minus SSC. SST is SSC minus SST minus SSC. This is also one of the parameter to find the ANOVA classification. Now we will be moving on to the major step, which is our ANOVA table. ANOVA table looks like this, and the source, the columns are denoted here. The first one is source of variations, degrees of freedom, sum of the squares, mean sum of the squares, variance ratio, which is will be using F test, and the table value. Here, since it is a one-way classification, we will be having the columns and the errors alone. Degrees of freedom corresponding to the column is c minus 1, corresponding to the error is n minus c. And sum of the squares, which we have calculated in the steps, as SSC and SSE. And also means of the sum of the squares we have calculated in the steps, which is MSC and MSE. And whichever value is bigger, which will be on the numerator, and whichever value is low, which will be on the denominator for the F test. As usually, while conducting F test itself, we have explained to calculate the variance ratio, the greater number will be on the numerator and the smaller number will be on the denominator. This is how we do for F test. And finally, the table value is calculated accordingly to the greater number as the row 1 value and smaller number as the row 2 value. So table value has been found using the table for F distribution. And in the conclusion, what we will say, if F calculated is less than the F tabulated value, we will be accepting the null hypothesis, and F calculated is greater than the tabulated value, we will be rejecting the null hypothesis as usually. Conclusion remains the same for all kind of design of experiments, but the only thing we need to notice the ANOVA table. So this is the major steps or the procedures which we have involved in the one-way ANOVA classification. We will continue with the problem in the next class. Thank you.